Hey everyone, and welcome. Today we are going deep on a really cool topic. How a tiny little computer, the Raspberry Pi Pico, can be turned into a brain powerful enough to control some serious industrial-grade machines.
I know. It seems a little crazy, right? How can this thing, something you can literally hide in the palm of your hand, tell some massive piece of factory equipment what to do? Well, the secret is a clever little component that acts as a translator between the tiny, low-power world of digital electronics and the high-power, real, physical world.
To make that connection happen, first you need some muscle. And in our world, that electronic muscle comes in the form of something called a relay.
Okay, so a relay is basically an electronic switch, but it has a kind of superpower. The two circuits it's connecting are completely, physically and electrically separated from each other. This means our delicate little Pico can tell a huge, power-hungry motor to kick on without any risk of getting, totally fried. It's the ultimate go-between.
And relays really only have two basic settings. Normally open means the switch is off until you tell it to turn on. Normally closed is the opposite. It's on by default and you have to send a signal to turn it off. This simple on-off logic is the bedrock of all industrial control, and it's absolutely critical for building fail-safe systems. You might want a critical safety valve to be normally closed, so if the power ever dies, it automatically slams shut.
And check this out. This is how engineers have been mapping out that logic for decades. It's called a ladder diagram, and it's basically the original programming language for industrial automation. Each rung on the ladder is a simple logical step, like if this switch is on and that sensor is off, then turn on this pump. It all comes back to those simple normally open and normally closed ideas.
All right, so we've got our muscle, the relay. But every muscle needs a brain to tell it what to do. And that's where our little hero, the Raspberry Pi Pico, steps in.
For this entire project, the brain of the operation is the Raspberry Pi Pico. It's this tiny, super affordable but surprisingly powerful little computer that we can program to control our relays with all sorts of complex timing and logic, stuff that a simple on-off switch could never even dream of doing.
So now we have a brain, and we have a muscle. This is the moment where we make that jump from a fun little project on a workbench to really understanding the backbone of modern industry.
I mean, what if you're not just controlling a single motor, but an entire assembly line? You might need hundreds, maybe even thousands of these little control circuits working together in perfect harmony in a really harsh environment. Let's be honest, a hobby breadboard and some jumper wires, they're just not going to cut it.
You get this. This is a programmable logic controller, or a PLC. Just think of it as the rugged, up-armored, industrial-strength version of our Pico and relay setup, but scaled up massively. These things are built like tanks to survive insane temperatures, electrical interference, and constant vibration. They are the workhorses that run pretty much every factory you can imagine.
And here's the really exciting part. The core ideas behind that expensive industrial PLC are exactly the same things we're playing with here. And thanks to modern electronics, we can actually build our own working version of one. So to turn our Pico into a little PLC, you just need a handful of off-the-shelf parts. The screw terminal board makes your connections nice and solid. An opto-isolator board is extra protection. It uses a tiny beam of light to send signals, which means total electrical isolation for the Pico. Then you've got your relay module for the muscle and a converter, so you can power the whole thing from a standard 24-volt industrial power source.
But the hardware is only half the story. The real magic is in the software. There's this amazing open-source tool called OpenPLC Editor, and it lets us program our little Pico using the exact same industry-standard languages, like those ladder diagrams we saw, that the pros use to program those giant, expensive PLCs.
Okay, so we've built our controller, but in a factory, nothing ever works alone. Our PLC needs to talk to sensors, motors, and other controllers. They all need to speak the same language.
And for decades, that language has been Modbus. It was developed way back in 1979, and it's a super simple but incredibly reliable way for machines to talk. It's based on a master-slave idea. One master device, like our Pico PLC, can ask for information from, or send commands to, a bunch of slave devices on the network.
And this table here really breaks it down. Modbus isn't just a concept, it's a set of very specific commands. For example, function code 01 is basically the master asking a slave, hey, let me read the status of your switches, or coils. Function code 03 is like saying, tell me the numbers you have stored in your memory, or holding registers. It's a simple universal dictionary for all this industrial gear.
So building this system sounds pretty straightforward, right? Well, this is where we hit our first major roadblock. A classic problem you run into when you're working with these tiny computers. And that problem is memory.
256 kilobytes. That is the total amount of usable memory, or SRAM, on the Raspberry Pi Pico. That's it. And that incredibly tiny space has to hold your entire program and give it enough elbow room to actually run. This is where things can get tricky. This quote from a developer just captures the frustration perfectly. They did the math. They checked the free space. They saw they had way more than enough room for the next thing they needed to do. And the program still crashed. So what gives?
Let's use an analogy to explain what's going on. Imagine the Pico's memory is one long bookshelf. As your program is running, it needs to store things, data, variables, whatever. Each one of those is like a book of a certain size that it places on the shelf. So, as your program runs, it puts some books on the shelf. Then, when it's done with that data, it takes those books off, leaving these little empty gaps all over the place. Now here's the problem. Let's say you suddenly need to add one very large book, like that 115,000 byte screen buffer. You can add up all the little empty gaps on your shelf, and you have more than enough total space. But if no single gap is big enough to fit that one big book, you are out of luck. The book won't fit, and that is memory fragmentation. And this is what makes it so incredibly frustrating to debug. The error message doesn't say you're out of memory. It often shows up as some totally bizarre network error, like this one. You see this and you immediately think your Wi-Fi dropped, but it has nothing to do with the network. The real problem was the system couldn't find a big enough unbroken block of memory, so managing not just how much memory you use, but when and in what order you use it is a huge part of the game.
So let's just recap the journey here. We started with the electronic muscles, the relays, that connect our digital world to the physical one. We gave it an accessible brain with the Raspberry Pi Pico. We learned that PLCs are just the super tough industrial version of that same idea. We found out that Modbus is the universal language they all speak. And, maybe most importantly, we saw that winning in this space means mastering real-world problems like memory fragmentation.
You know, for the first time ever, the tools and the knowledge that you need to build and prototype these industrial-level control systems are incredibly cheap and available to everyone. The barrier to entry has basically disappeared. So the only real question left is, what are you going to build?